This is Young Kim from Seoul National University. Let me introduce our paper, Bridging the Gap Between Model Explanations in Partially Annotated Multi-Label Classification. Partially annotated multi-label classification has emerged recently to reduce the annotation cost of multi-label classification. Rather than annotating all categories, it annotates a part of categories for each training image, like column B or C. In a nutshell, we investigated the impact of false negative labels, which occurs when assuming unobserved labels as negatives. From the view of the model explanation, we observed that false negative labels do not affect the model's localization ability. Then we proposed a simple but effective method to bridge the gap between model explanations. Let's dive into more detail. When given partial annotation, the baseline approach to training the multi-label classification models is assuming unannotated labels as negative labels. In other words, all empty cells in the label vector are filled with 0. This is because the number of negative labels is much greater than the number of positive labels in a multi-label setting. However, it introduces label noise. For example, this image contains a horse, but the label is wrongly annotated as negative. This kind of false negative label damages the classification performance during the training. Previous literature in this task usually focus on removing the false negative labels in order to minimize the damage to the model. In this paper, we look at the false negative labels from the view of model explanation, and we investigated how these false negative labels affect the model explanations. To perform a controlled experiment, we trained two models, one with full annotation and the other with partial annotation. Then the first model is trained without false negative labels, and the second model is trained with false negative labels. After the training finished, we compared the model output. Specifically, we compared the class activation map result, which is the method to convey the model explanation. The result is as follows. The first column shows an input image, and the following columns show the CAM output of the models trained with full annotation and partial annotation, respectively. From this, we observed that the model trained with partial annotation is still able to highlight the regions where the object exists. At the same time, the intensity value of the corresponding region is greatly decreased. This implies that the false negative labels included in partial annotation do not affect the model's localization ability. Based on this observation, we came up with the idea that we can easily bridge the gap between these two models' explanation by compensating for the decreased intensity score. To bridge the explanation gap, we first modified the CNN architecture slightly. By moving the last fully connected layer in front of the global average pooling operation and replacing it with a one-by-one convolutional layer, we can obtain a class activation map directly during a forward pass. We can also obtain a log score by averaging the intensity scores from class activation map. Then we propose a novel piecewise linear function called boostLu because of its shape similarity with ReLU function. We previously observed that the highlighted region has positive intensity scores, while other regions have negative intensity scores. So the proposed function is designed to keep the negative intensity score unchanged while multiplying the positive intensity score by alpha times. This is the overall pipeline of the proposed method. First, we obtain class activation map by feeding an image into CNN network. Then we apply boostLu function to eliminate wisely on the CAM to obtain the boosted CAM result. The final classification is performed by further applying global average pooling and sigmoid activation on the boosted cam. As can be seen, our proposed method is very simple. Also, it is very effective, leading to performance improvement. First, if we apply the proposed boost LU function to the baseline model only during inference, we observed that the test performance is increased without additional training. When we also apply boost LU function during training and retrain the model, its test performance is further improved. It can be confirmed that the proposed boost LU function contributes to the model performance improvement both during training and inference. Compared with other methods from the literature, our proposed method achieves state-of-the-art performance both on single positive label setting and open images, which is a large-scale multi-label dataset given only partial annotation. From the qualitative results, we can see that the proposed boost LU helps the model to achieve the good explanation results. This is the end of the presentation. Thanks for listening. You can also check the source code by scanning this QR code.